Hello guys, welcome back. We are starting new unit. This is aromatic hydrocarbons. So aromatic hydrocarbons, the word comes from aroma. So before it was known, before they found out what is actually aromaticity, so a lot of these compounds were there, like benzene, like compound, very nice smell they used to have. All this perfume, that smell, we call it aroma. So that's why they were called, class of compound, they are called aromatic. And if in school you must have seen for aromatic compounds, they do testing. What is the testing they do? It burns with shooty flame. Other normal hydrocarbons, they don't burn with shooty flame. So that means they go for complete combustion. With these aromatic hydrocarbons, they don't burn easily. So they leave unburnt carbons. And because they leave unburnt carbons, so that comes a shoot. So why does it happen? Because it is very stable. Aromatic compounds are very stable. They don't react easily with oxygen. See, combustion is reaction with oxygen. So some of them remains unreacted, and that's why you get shooty flame. Right? One exception of a non-aromatic compound which gives a lot of shooty flame is camphor. But camphor, if you see, a cyclic compound, it's a very, very stable compound. And that's why it doesn't burn so very effectively, and that's why it gives shooty flame. Okay? Alright. Let's talk about the aromaticity. So first example is what comes into mind when you talk about aromatic compound is benzene. So benzene, these are the two resonance structures, and this is what we can show. We have talked a lot about resonance conjugation, all this. So structure is neither this nor this nor this, but it's kind of, I cannot show in the real way, so I am trying to show with as many as possible. But basically it is like this. Okay, it's a very simple thing you have to understand. All these carbons are planar. They are all on the plane of paper. Okay, nothing is coming out. Molecule is planar. Very, very important. Then it has one p orbital which is perpendicular to the plane of paper or plane of molecule. Similarly, this p orbital, this p orbital, this p orbital, this p orbital, this p orbital. Now all of the p orbitals have one electron. So generally what we say, if two orbitals are next to each other, one electron, they will share and they form pi bond. But here it's not like that. This one has p orbital, this one has p orbital, this one has p orbital. So it says, why should I form bond only with you? This p electron in this p orbital, I will form bond with this also. So all these p orbitals have one electron, and all orbitals are overlapping. So electrons are being shared all over the ring. There is no separate two bonding. That's all it is. That's what makes it very, very stable. Now it's very stable. How do we know? Because it's not easy to break the aromaticity. Double bond. It's very reactive. You put bromine, immediately you see decoloration of water. Bromine water. You can put bromine in water, bromine in carbon tetrachloride. Immediately color disappears because bromine gets added. You add benzene, bromine in bromine water, bromine tetrachloride in benzene, nothing happens. Only if you put FeBr3, FeBr3 is a catalyst, Lewis acid catalyst, and you heat it up. It's not easy reaction, okay? You have to put a lot of hard work, and then this reaction happens. And that too, in this reaction also, this double bond is not lost. Molecule retains all its structures, very reactive. Only thing is, hydrogen has been replaced with bromine. So it undergoes substitution reaction and not addition reaction. This one is addition reaction, this one is substitution reaction, okay? Okay, right. Now how do we know it is stable? So they took a simple example. They took cyclohexene and reduced it. You put H2 so that it becomes cyclohexane. Now whenever the double bond is there, it gives it it's given instability. It's reactive because double bond is pi bond. So when you react with H2, it becomes cyclohexane. Some amount of energy is released. Right? This much amount of energy is released. Now they took benzene and then H2 is formed. So cyclohexane is being formed. Understand, this product is more stable than reactant. This way energy is being released. Now here also energy is being released. So cyclohexane is more stable than benzene. But this is expected because it does not have any pi bonds. Whenever pi bond is there, it makes it unstable. But if you see here, it is having stability of minus 208 kilojoules. Theoretically, if you see, benzene is like cyclohexatriene. So if cyclohexene one double bond gets reduced, H2 gets added, this much energy is being released. So here if reduction happens, it should be almost 120. So 120 into 3, it should release almost 360 kilojoules per mole. That much amount of energy it should release. But it's releasing only 208. That means this molecule did not have that much energy. If it does not have that much energy, from where it will release? So when the molecule was formed itself, it was not, it has lost lot of energy. So the extra energy which it should have, but it is not having, that is called as resonance energy. Okay. So the stability of benzening is because of resonance energy. Resonance energy is the energy which it is not having. And this extra stability you can say because conjugation, we know it's conjugating, all the orbitals are conjugating. But it's not that. If you just take a hexatriene normal molecule, this also undergoes addition reaction. This will have a huge amount of delta H value of reduction. When you reduce it with H2, this delta H will be very high, right? It's not like benzene. So benzene has something else which makes it very stable. What is that thing is called as resonance energy. So resonance energy comes because of aromaticity. Now to understand aromaticity, actually quantum mechanics come into picture. We will study in your PG all those explanation. But we will study here very, very superficially. So the extra energy which molecule does not have is called resonance energy. So you can say, okay, it is cyclic system and conjugated, so it might be very stable. But it's not that simple. This molecule, this molecule is cyclobutadiene. 2 ines are there, cyclobutadiene. Highly unstable actually. So very unstable that if at all it is formed, it loses its planarity. You will start seeing double bond and single bond separation. That means you will see that this bond is longer and then Y. If X and Y are there, X is longer than Y. But in benzene, if you know, there is no X and Y. They have all lost their character. X is equal to Y. The bond length has been found. They are all equal everywhere. And bond length has been found to be intermediate between single and double bond. Okay. Bond length is neither as long as single bond nor as small as double bond. It is intermediate between them. So the bond order is considered for benzene 1.5. Very clear cut conjugation is there. There is no separate single and double bond. But here, it forms with great difficulty. And if at all it is formed in a very short period of time. Actually, there is one topic which we are not supposed to do right now, but I'll introduce that word. There is something called as anti-aromatic. One thing is if it is aromatic, very stable. Then non-aromatic means not stable. Non-aromatic means not stable. But when it is anti-aromatic, it is highly unstable. When it is anti-aromatic, it is highly unstable. So that means it will rather prefer to be non-aromatic than anti-aromatic. So this molecule is actually anti-aromatic. I will talk about it later. Aromatic means it has to follow 4n plus 2 rule. But if it follows 4n rule, then it is anti-aromatic. So this is anti-aromatic. So anti-aromatic is highly unstable. So it will rather say I will become non-aromatic. So it loses, you will get single bond and double bond. It loses basically its planarity. One carbon comes up, one remains down, up and down, so that conjugation is lost. Similarly, if you see this cyclooctatetraene, highly unstable. This also actually anti-aromatic system. Right now you don't need to know about anti-aromatic. You can say they are non-aromatic system. So aromaticity, not just cyclic system which is conjugated. It has lot of other things. So what are the basic criteria for aromaticity? So I never ask you in examination, I will not ask you give me all the criteria for aromaticity like history question. No. I'll give you molecule and ask you is this aromatic or not. Then you have to tell all these points, 4 points, and then explain that this fulfills all these properties or it does not, it fulfills these three properties but does not fulfill this fourth property, and therefore it is non-aromatic, right? First is molecule should be cyclic. So benzene, we know it is cyclic. Second, very important, molecule should be planar. You understand what is planar? Planar means all these four carbons should be on the paper in the same plane. If some carbon is coming up or coming down, they lose the planarity. That means p orbital are not parallel to each other, then aromaticity is lost. When it is planar, what happens? This p orbital is perpendicular, this p orbital is perpendicular, this p orbital is perpendicular, this p orbital is perpendicular. So all the p orbitals are parallel. When they are parallel, they share the electrons, they overlap. If they are not parallel, they will not overlap, and so no aromaticity. So very important point is stuff like people don't understand what is planar. Third is molecule should be conjugated. Conjugated means what? It is basically like this. P orbital can move here, this p orbital can move here, like that, okay? Basically it says all the neighboring carbon atoms should have p orbital, okay? And in the p orbital, it may have electron, it may not have electron. It may have one electron, it may have two electron. But no atom should be free. So this pi bond is what? Pi bond is unhybridized p orbital. You know that. Pi bond is unhybridized p orbital. So it has p orbital, it has p orbital, p orbital, p orbital. So when all of them are having p orbitals with 1 electron, 0 electron or 2 electrons, okay, then it is conjugated. All the neighboring carbon atoms should have that p1. And last one, very important, this one is called as Huckel's rule. Should follow Huckel's rules, okay, not electrons, Huckel's rules. So it says the number of pi electrons should follow 4n plus 2 electrons. So if you see this, how many electrons are there? 1, 2, 3, 4. So I will explain you what is 4n plus 2, then it will become clearer to you. See, what is this 4n plus 2 rule? So this n is any integer, positive integer. So it can be 0, 1, 2, 3, 4. So if n is equal to 0, 4n plus 2 becomes 4 into 0 is 4 into 0 is 0 plus 2 is 2. When n is equal to 1, it becomes 6. When n is equal to 2, it becomes 10 electrons. So it should have either, the number of pi electrons should be either 2, 6 or 10. Now if you see this benzene, how many pi electrons are there? 1, 2, 3, 4, 5, 6. So it is following 4n plus 2 rule where n is equal to 1. But whereas this system, if you see, it is having 4 electrons. So it is not following 4n plus 2. This is having 8 electrons. It is not following 4n plus 2 rule. Actually, if you see, this is following 4n rule. This is following 4n rule. 4n rule means it is anti-aromatic. Anti-aromatic is much more unstable than non-aromatic. So system will never stay in anti-aromatic. If any system like this, you form it with great difficulty, immediately it will lose its planarity. So that double bond and single bond are separate. That is called as anti-aromatic. Okay. So let us see. I wanted to explain all this planarity and all. If you see this molecule, it is cyclodeca pentaene. Is that right word? Triene. Yeah. Pentaene. Basically 5 double bonds are there. It is 10-membered ring. See this molecule, no? Because if molecule stays like this, it will be planar. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of them are on the paper. But when this happens, these two hydrogen come next to each other, they start fighting. Immediately this molecule is pushed apart. This carbon is pushed apart, this carbon is pushed up. Carbon is pushed apart. And immediately aromaticity is lost. So you'll see that this molecule is not very aromatic. It's not anti-aromatic, but it's non-aromatic because planarity is lost. And that's why you'll not find very commonly in nature cyclodecapentaene. But you can see naphthalene. This molecule is naphthalene. Everybody knows that. So naphthalene is 2 benzene rings together. Only difference between this and this is there is a bond here. But this bond makes lot of difference. That 2 hydrogens which are fighting with each other, those 2 hydrogens are not there. So this molecule gives it planarity, and this is very stable. Naphthalene, you know, you put in the toilet that white balls, they are all naphthalene. Very stable aromaticity. aromatic. So I was talking about aromatic. I told you already about the Huckel. So this one is aromatic because it has 6 electrons, not this and this. Okay. Next is conjugated system. I talked about conjugated system. Conjugated means each of them should have p orbital. Now this one has p orbital, because sp2 hybridized, one p orbital is anhybridized, one p orbital anhybridized. This one is sp3 hybridized orbital, so no p orbital. But if you see this molecule is aromatic. So if I ask you what is this cyclopropyl carbocation, is it aromatic or not, you have to explain through all the ways. You have to tell yes it is, because it is cyclic, it is planar, very small, it cannot lose its planarity. It is conjugated. Why you will say conjugated? This one has p orbital, this one has p orbital. Both of them have 1 electron. And positive charge also means there is a p orbital, but no electron. But that does not matter. No electron is fine. It is conjugated. Now electron can come here. You understand? Electron can come here. You are having a conjugated system. You are having a conjugated system. Then again this comes here. Sorry. Yeah. So you are getting conjugated system where positive charge is being delocalized. And apart from that, it is following 4n plus 2 Huckel's rule. Okay, why? Because when n is equal to 0, the 4n plus 2 becomes 2 electrons. So it is having 2 pi electrons. Whereas this system, not very, very unstable, does not form only. Why? Because it is cyclic, planar, conjugated, because p orbital, p orbital, but 1, 2, 3, 4. Minus charge means 2 electrons are there. So it is having 4 electrons, so it is following 4n rule and not 4n plus 2 rule. Similarly, this system is non-aromatic because it's not conjugated. This pi bond cannot move here, right? Pi bond cannot move here because it is sp3 hybridized. But if you put a positive charge, it becomes conjugated. But it is not aromatic. Why? Because it is having 4n electrons, not 4n plus 2. But this system is aromatic. Now here there is a p orbital with 2 electrons, right? So it does not matter. P orbital can have 1 electron, 0 electron, 2 electrons. It is having 2 electrons, but now how many electrons it becomes? 1, 2, 3, 4, 5, 6. So it is following Huckel's rule. It is planar, it is cyclic and conjugated. Now we'll see some heterocyclic system. See this pyridine. It's a very, very important molecule in organic chemistry. It's the base. Okay. Now this nitrogen is sp2 hybridized. So when it is sp2 hybridized, all the sp2 hybridized orbitals will be trigonal planar, like that, and like that. So all of them are in the same plane, 120 degrees to each other, and it has a p orbital which is parallel. So this p orbital, this lone pair electron in the sp2 hybridized orbital is perpendicular to this p orbital, this p orbital, this p, this p, this p. Okay, so they don't overlap. Okay, they don't overlap. Very important point. So this system is still aromatic because we are not bothered about this. This is not disturbing the ring. Aromatic electron is not overlapping with this. So you cannot say it is having 6 plus 2, 8 electrons. So it is not following 4n plus 2 rule. No, these 2 electrons are not part of the ring. So we don't bother about them. We bother only about this 6 electrons. So it is following 4n plus 2 rule. And so it is aromatic. But when you see pyrrole, that was pyridine, this is pyrrole. Pyrrole NH is there and lone pair is there. Basically a lone pair is drawn here. And this is sp3 hybridized, so it is 109 degrees. So it is not exactly parallel to this, but little bit tilted, but they overlap, not 100%, but to a large extent it overlaps, okay? And when it overlaps, now what is happening? These 2 electrons. So it's a cyclic system, planar and conjugated. So this one has p orbital, this one has p orbital, p orbital, p orbital, p orbital. So electrons can go from here to here, it can come here, here to here, here to here, here to here, okay? So it's a conjugated system, right? And therefore it is aromatic, not as much as benzene, but even not as much as pyridine. Actually it's less aromatic than pyridine, but it is still aromatic. And interestingly, how we know it is aromatic? If you see the basicity between these two, this is much more basic than this. This is not basic, neutral it is. Why? Because it has lone pair which is outside the ring. So it is available to attack the proton. What is base? Base is one which attacks proton. But here this lone pair of electron is part of the system. And when it is part of the system, it cannot attack proton, okay? And because it's not available outside, it's in the ring, and therefore it is much lesser basic than this. Other examples of heteroaromatic systems are furan and thiophene. Furan is oxygen, thiophene is sulfur. Right. Next we are going to talk about electrophilic substitution reaction. Okay. Now I told you how the benzene looks like. Benzene is a ring. All of these are the p orbitals which are perpendicular to the ring. So electrons are there. So if this is benzene ring, lot of electron density top and bottom of the ring. Lot of electron density is there. So if electron density is there, if any electrophile comes, you have to remember this word, electrophiles. Phile means loving. Electro means electron. Electron loving system. So whenever you think about electrophile, when you think about electrophilic substitution reaction, think about electrophile, and whenever you think about electrophile, think about E+. So now because on the benzene ring lot of electron density is there, it attacks E+. So it undergoes electrophilic substitution reaction. Okay? Always remember when you write a reaction, negative charge chases positive charge. You cannot show bond like this. Plus will never attack negative. Always negative will attack positive. So first what step? This one moves and attacks E+. You are having H and E, you are having positive charge here. Right? And this double bond moves here. You are getting a positive charge here. Okay? And then this moves here, you are getting positive charge here. So basically you are having positive charge all across the ring. E+ is there. And the next step, base comes, takes away this proton. Why it takes away this proton? Because initially it was very stable, aromatic. Now it is having positive charge, makes it unstable, and more than that, aromaticity is lost. So it wants to gain back aromaticity. So even very simple, pathetic, hopeless, most hopeless base, if you put, actually E+ when you generate, some counter anion will be there. That itself is good enough to take this proton. Means this proton is dying to be taken away, so that this comes here and becomes stable again. Right? Examples of electrophilic substitution reactions. First one is Friedel-Crafts alkylation reaction. So Friedel and Crafts were two scientists. Okay, they together discovered. So they took benzene and reacted with alkyl halide in presence of Lewis acid catalyst. Why it is called Lewis? Spelling you should know, Lewis. Okay, because its octet is not complete. Aluminium has 3 electrons, group 13. Okay, atomic number is also 13. So 2, 8, 3. 3 electrons are there. All 3 chlorine contribute 1 electron. So 3 plus 3, 6 electrons. So octet is not complete. So it can accept lone pair of electron. So we add them as catalyst. Catalyst means two things. One is you add very small amount. Second thing is at the end of the reaction it should regenerate so that it keeps getting used again and again. And what you get is alkyl part gets added and HX is removed, this X. So like benzene is there. You react with CH3Cl. In presence of AlCl3 you get this and CH3. Benzene ring you react with CH3CH2Cl with AlCl3. So this part goes and attacks this carbon. This Cl minus leaves. Carbon valence is only 4. Many times students write in examination CH3CH2, which makes no sense. Carbon cannot have 5 valency. Okay, so it has to be CH2 CH3. Right? We look at the mechanism. Yeah. Mechanism, always the first step is generation of electrophile. So first you are having this alkyl halide. Now this chlorine is there, it's electronegative. So it pulls the electron towards itself. So it has certain amount of negative, it has certain amount of positive. By itself it is an electrophile. Benzene should be able to attack here. But it's not that reactive that benzene will go and attack. You have to make it more powerful electrophile. So this reacts with AlCl3. AlCl3, as I told you, is a Lewis acid. So this lone pair attacks here and you're getting Cl plus, Al gets negative charge. Then this benzene attacks here. This AlCl4 minus leaves and you are forming bond here with this carbon, CH2, CH3 hydrogen there, and you get a positive charge here. Then AlCl, I told AlCl3 is a catalyst, so it should come back. So immediately as soon as AlCl4 minus is formed, not stable, Cl minus comes out and you get AlCl3 plus Cl minus. Maybe I should have shown you. Okay, it's like this, AlCl4, okay, Cl3 minus is there, so this Cl minus comes out and you're getting AlCl3 plus Cl minus, right? And then you have to always show, see, this is not part of mechanism, but you have to always show how the resonance is happening. Why this reaction is happening is because even after getting positive charge, it's not that unstable. Because system is conjugated, this positive charge is not localized on one carbon, it is delocalized. So if it's delocalized, then it's okay. If it's only one place, positive charge, highly unstable. But if it's spread around, not so much. So this pi bond comes here, you get a positive charge. Then this pi bond comes here, you get a positive charge. So overall I can show like that, and you get positive charge, you get this. Then the last step is the Cl minus. I told you Cl minus is a pathetic base, most horrible base. Imagine HCl is a very strong acid. So HCl is very strong acid when Cl minus is very, very weak base. But even that is able to take away this proton. So this comes and you get back this molecule. Okay. Next is Friedel-Crafts acylation reaction. So Friedel-Crafts acylation reaction is you are adding acyl part. Now this is called as acyl part. If you put acyl Cl here, acyl chloride, acyl bromide. Then acid is there, acid anhydride is there, ester is there. This part is acyl. So you react with RCOCl or RCOBr. In presence of AlCl3, you get C double bond O R plus HX, right? So again, very similar to that mechanism. So you example is here. You take this, react with CH3COCl. Now Cl is more electronegative, so it pulls the electron towards itself. So you get positive polarity, negative polarity. So this is an electrophile, this attacks and Cl minus leaves. It's not that easy because it has to be powerful electrophile. So you need to react with AlCl3 and then this reaction happens. So the mechanism is this reacts with AlCl3 first. So chlorine has lone pair, it goes and attacks aluminium and you are having CH3 C double bond O Cl plus AlCl3 minus. So since chlorine has attacked, you understand, initially both electrons are on chlorine, it was neutral. Now it forms a bond. So chlorine keeps one electron and one electron it gives to aluminium. See, bond means chlorine kept one electron, gave one electron to aluminium. So aluminium got extra electron, chlorine lost one electron, so chlorine is having positive charge, this is negative charge. Now imagine chlorine was there already electronegative, now it got positive charge, much more electronegative. So it is pulling electron very strongly, so it has become quite positive center. And then what happens is this double bond, say there are many ways of showing the mechanism. Generally I always liked showing, I always used to show like this, but this looks better, okay, more neat, but both are fine. So oxygen lone pair comes and this comes out and you get this one. It's a powerful electrophile. This benzene attacks, you get C double O CH3. Now you have to show all this delocalization of electrons, and then Cl minus, I was talking about it previously also, it comes and takes a proton and bond comes here and you get this. Okay. Next is nitration reaction. So nitration reaction, you use HNO3 and catalytic amount of H2SO4 and you get nitro. So most of the competition examination they ask this question, what is the electrophile in nitration reaction? You cannot write HNO3. That's not electrophile. Electrophile is NO2 plus. NO2 plus is generated in situ. IN space SITU. In situ means in the reaction chamber it is generated. How? So you react HNO3 with H2SO4. Now H2SO4 is stronger acid than HNO3. So when H2SO4 is stronger acid, then this acts as acid and HNO3 acts as a base. You understand this part? So even though HNO3 is acid, in general what we think about acid, but here HNO3 acts as a base. What does it mean? Acid which gives proton. So here H2SO4 gives proton. Base which accepts proton. So this one accepts proton. So first lone pair goes and attacks here, and this comes here. SO4 minus is lost. HSO4 minus is lost, and you are getting OH2 plus. This minus comes here, OH2 plus. That means water is lost here. Okay, water is lost here, and you get NO2 plus. Remember this. First step is generation electrophile. NO2 plus is the electrophile. Okay, plus HSO4 minus I should write here. Next step, what happens? All that I told. Next step, second step, what happens? This NO2 plus is being attacked by benzene ring. Attacks the benzene ring, and you're getting positive charge here. Now you get positive charge. You have to show all the resonance stabilization. This comes here, this comes here, this comes here. And then I showed you HSO4 minus is a pathetic weak base, even weaker than Cl minus, because H2SO4 is queen of acids, very strong. And so HSO4 minus is very weak conjugate base, but that's good enough. Takes away this proton, this bond comes here, and you get nitrate product. Sulfonation, you react with SO3 in presence of H2SO4, you get SO3H. Mechanism you write as assignment. Halogenation. So you want to halogenate, you want to chlorinate or brominate. So if you want to chlorinate, you put Cl2 with FeCl3. FeCl3 also same, acts as a